Welcome to the next lecture of cooling tower under the edges of chemical process utilities. Now in this particular chapter we are going to discuss about the various concepts of heat transfer in cooling tower and different components. Now before we going to have a broad discussion about this, let's have a brief outlook that what we discussed in the previous lecture. So in the previous lecture we discussed about the theory, what is the theory of cooling tower. We performed some basic calculation, those related to the cooling tower. These attributed to the moisture content, that is pertaining to the absolute humidity, relative humidity, mixing ratio. We discussed about the vapor pressure. We discussed about the dew point, dry bulb temperature, wet bulb temperature. We had one humidity calculation for reference. Then we had a discussion about the total heat and enthalpy apart from the broad discussion about the psychrometric chart. Now in this particular lecture, we will discuss about the various concepts attributed to the heat transfer in cooling towers. I will discuss about the cooling tower, what are the different elements of cooling tower. Now since as name implies, it may have some heat transfer aspects. So what is the heat transfer aspect in the cooling tower? We are going to discuss different modes of heat transfer. We will discuss about the heat transfer theory with respect to the overall heat transfer coefficient and Merkel's heat transfer theory. So let's have discussion about the cooling tower. Now it has the role of rejecting heat collected during the space cooling process to the ambient atmosphere. Now as the condenser water flows through the cooling tower, the heat is rejected to the ambient air and the condenser water is cooled. Now primarily through evaporation of a small percentage of total water flow. Now the evaporation is the process by which heat is absorbed by the air and remaining condenser water is cooled to the desired leaving temperature. So by this way, it's a very important phenomena in chemical engineering aspect. Now when we talk about the various elements of cooling tower, there are different elements required for every type of cooling tower. Now in this particular figure, like we must have an evaporation and drift. Apart from this, one must have a wet deck filling because it is duly supported by air. So air inlet must be there. Similarly, the water inlet should be there, and because it's a phenomena of heat transfer between air and water, so we must have some makeup water, and there is a basin, and this water is coming out with the help of a blow down, and at the outset or at the upper part of this cooling tower we are having the outlet for the air. Now this is more, you can say, the schematic, precise schematic arrangement of a typical mechanical draft of cooling tower. Here you see that it is supported by a fan to support the air outlet. We are having a proper casing, and this if you recall that here we are having this water, then water distribution system. This is through here you are distributing the water, and there are certain packings for enhancing the overall heat transfer. There are certain louvers through which you are supplying the inlet air, and there is a port for this makeup water with the water sensor or water level indicator. Then there are certain overflow because sometimes there may be oversupply of water, so there must be certain discharge port for the overflow connection, and this is the cold water basin. Now because we are discussing some elements of cooling tower, so as you recall that we are having some packing over here. Now this fill or packing, it is the heat transfer media in the cooling tower, and these fills are designed to maximize the contact between the return condenser water and the ambient temperature. Now, the better is the contact, the better will be the evaporation and the heat transfer. Then there is a wet deck. You see that here we are having this wet deck. Now, this is also known as the hot water distribution. It is the pan or basin with metering outlet or spray nozzle. Now, here you see that these are the spray nozzle. These spray nozzles are designed to provide an even distribution of the return condenser water entering filling operation. Then there is a cold water basin. If you see that here we are having the cold water basin. Now, it is an integral part of the tower or separate sump. It collects the water passing through the tower for supply to system by condenser water pump. Now, this basin must also be sized to contain enough water to supply the condenser water system until the pump returns water to the tower. Then there must be fan. Here we are having the fan. Now, all cooling towers, they use the mechanical draft tower that use one or more fans to provide the airflow through the tower. Then there are certain inlet louvers. Now, here you see that there are certain inlet louvers. Now, it acts to force the air entering into the tower as straight or even flow pattern. Then there is a drift eliminator. Now, it is designed to trap and remove any entrained water droplet before entering to the tower, leaving air stream. Then obviously all these things are there, then we must have a casing or a shell. The structure enclosing the heat transfer process reinforced as necessary to carry the other main items. Apart from this, these cooling tower, they are having some air inlet and outlet. Now, these are positioned at which the cooler air enters and warm air leaves the tower. Now, in natural draft tower, the inlet is normally protected by drip-proof louvers and outlet by the suitable grills, whereas in the induced draft fan is used the outlet as fan casing. With forced draft, the fan casing provide the inlet. Now, let us talk about the cooling tower heat transfer. The heat is transferred from water droplets to the surrounding air by both the sensible and latent heat transfer process. Now, if we consider a single droplet of water, here you are having this single droplet of water in the tower, and this is surrounded by the unsaturated air. You see that here we are supplying some unsaturated air. Now, here you see that the heat is lost by the evaporation, and this convected heat is transferred to the surface, and then this is the radiant heat. Now, the heat transfer, the question arises that how heat transfer can be done. Now, the heat transfer can be done in various ways. One is by the radiation from surface to droplet, and this is neglected amount of heat flow. Now, here you see that. Now, by conduction and convection between water and air, the amount of heat transfer will depend upon the temperature of air and water. It is significantly 1/4 to 1/3 proportion of the whole. Another mode of heat transfer is by evaporation. This is accounts for majority of heat transfer and is the reason why the entire process is termed as evaporative cooling. Now, here you see that heat lost by the evaporation. Now, the principle, when we talk about the principles of evaporation in cooling tower, the evaporation occurs when air and water are in contact, usually caused by the difference in pressure of water vapor at the surface of water and in the air. And these vapor pressures are function of the water temperature and the degree of saturation of the air respectively. Now, in a cooling tower, the water and air stream, they are generally opposed, so that the cooled water leaving the bottom of the pack it is in contact with the entering air, and that in other terms you can say they are in the counter current manner, they flow in the counter current manner. Similarly, hot water entering the pack will be in contact with the warm air leaving the pack. The evaporation usually will take place throughout the pack, and it should be remarkably noted that at the top of the pack the air is nearly saturated and usually compensated for by the high water temperature and consequently high vapor pressure. The amount of evaporation which takes place depends on a number of factors, including the total surface area of the water present to the air and the amount of air flowing. And that is why the packing design is so important. The greater the air flow, the more cooling is achieved, and this is because as the air rate increases, the effect of water on its temperature and humidification will become less, and the partial pressure differences throughout the pack will be increased. The wet bulb temperature of the entering air has a very important effect. The lower the wet bulb temperature produces a lower water off temperature. Come back to this figure again. The heat transfer mechanism, here now we are discussing the heat transfer mechanism between the water droplet and air. The mechanism of convective heat transfer from solid or liquid to air or gases is critically dependent on the behavior of a nearly stagnant layer of air or gas at the surface of the solid and liquid. Now, this layer is referred as the boundary layer or film, which usually affect the heat transfer depending on the heat transfer coefficient of the film. So, we are talking about this particular layer. Now, there are a couple of factors which can influence the convective heat transfer. Now, those are one is the temperature difference, and second is the fluid properties such as velocity, thermal conductivity, thermal expansivity, specific heat capacity, kinetic viscosity, dynamic viscosity and density. Now, let us talk about the heat transfer theory. Now, in cooling tower, two fluids are involved. One is moisturized air, that is up to a certain saturation point, and the water which enters into the tower at higher temperature and leaves the tower at lower temperature. Now, mainly heat is transferred as latent heat or evaporative increment, and which is to be extracted from water as it flows through the tower. Now, roughly 75% or about 75% of total heat is transferred across the interface between the water and air. Now, this is the droplet and this is surrounded by air. So, this is the water droplet and this is air. So, this is the mode of this particular transfer is the diffusion or via diffusion of water vapor. Now, this is distributed to the bulk air by convection. So, first thing is that the diffusion, and then it is the convection. So, convective heat transfer applies. The balance heat is transferred by conduction and convection in between the water and air. So, the two mechanisms, that is mass and heat transfer, usually take place. Now, just because of mass of air, that is usually very much greater than the mass of water. Therefore, it may be assumed that no change occurred in the air condition. Now, the droplet is surrounded by the boundary layer of air, and the water vapor will be diffusing through at its rate of say watt per kilogram second. I mean, this is the droplet and surrounded by this air current of air. Now, if the specific latent heat of the diffusing vapor stream is lambda W, and that is referred as kilojoule per kilogram, then the rate of heat diffusing will be W into lambda W kilojoule per second or kilowatt. Now, as the wet bulb temperature is below the temperature of bulk air, then there will be a sensible heat flowing into the droplet at the rate of Q, and that is having the unit of kilojoule per second or kilowatt. Now, the wet bulb temperature will be equal at a point where this particular sensible heat is equal to the heat of diffusion, and this is the mathematical representation, that is Q is equal to W into delta lambda W, and that is equation number 1. Now, if we recall the heat transfer theory, now it says that Q is equal to alpha into A into T minus Ti into lambda W, that is equation number 2. Now, where the Q is the sensible heat flow rate in kilowatt, alpha is the film heat transfer coefficient, and it is having the unit of kilowatt per meter square Kelvin. A is the superficial area of drop, unit meter square. T is the bulk air dry bulb temperature, and Ti is the temperature at the interface between the air and water. Now, it is possible to express the rate at which the water vapor is diffusing from droplet either in terms of partial pressure or in terms of absolute humidity. So, if we take that water, this W is equal to kg into A into Pi minus Pg, that is equation number 3, where W is the rate of water diffusion, that is kilogram per second. This kg is the film coefficient of diffusion. Then Pi and Pg, they are the partial pressure at the interface and the bulk, and usually represented in the unit of kilopascal. Now, one can write this equation in terms of humidity, that is W is equal to K1G into A into Xi minus Xg, where this K1G is the mass transfer coefficient having the unit of kilogram per meter centimeter. Xi is the absolute humidity at the interface, that is obviously having the unit of kilogram per kilogram, and the Xg is the absolute humidity in the bulk air, and that is again the unit of kilogram per kilogram. Now, the terms in the equation from all these equations from equation number 1 to 4, that is T minus Ti or Pi minus Pg or Xi minus Xg, named as the temperature difference, vapor pressure difference, and absolute humidity respectively, and they are the driving force due to which heat transfer takes place. Now, obviously, when we are looking for this heat transfer aspect, then definitely there must be some driving force, and this is the way through which you can represent and you can analyze the scenario that how this heat transfer takes place. Now, if we substitute the values of Q and W from these previous two, equation number 2 and equation number 4 in very first equation, and that assuming that the water temperature at equilibrium is the wet bulb temperature of air, in that case Ti would be equal to Tg. Then we have Xi minus Xg is equal to alpha Ti minus Tg over K1G into lambda, and that is equation number 5. Now, the wet bulb temperature Tg, this also known as equilibrium temperature, it depends only upon the temperature and humidity of the air, and it is usually independent of the factor which might influence the thickness and resistance of air film in contact with water. Now, let us talk about the overall heat transfer coefficient. Now, as the actual temperature at the interface and contact area between the air and water cannot be determined normally by experiments, so overall coefficients are used. The heat transfer and diffusion from water to air, it depends upon the air film coefficient and alpha and K1G and the heat transfer coefficient of the water film. Now, this particular figure shows the heat transfer profile in cooling tower when water temperature below the dry bulb temperature. So, the overall heat transfer coefficient based on the temperature difference between the bulk water and bulk air is T minus small t, and overall diffusion coefficient is XW minus XG. So, here you see that we are having this air film and this is we are having this water film. Now, this we have to look at the sensible heat from bulk water, and this is the sensible heat from bulk air, and latent heat carried out by the vapor. Now, the overall heat transfer coefficient based on the temperature difference between the bulk water and the bulk air is T minus small t. Now, alpha is the thermal conductivity and K1G, as I just told you, is the diffusion coefficient. Now, the thickness of the film is primarily a function of mass velocity of the air passing in the film. Now, let us talk about the Markel's theory of heat transfer. For calculation of cooling tower performance by using heat transfer and mass transfer separately, the Markel's theory provides a simple version. According to this particular theory, the total heat transfer taking place at any position in the tower is proportional to the difference between the total heat of air at that particular point and the total heat of air saturated at the same temperature as the water, and that is Q is equal to Ka into A into Hw minus Hg, and that is equation number 6. Now, here Q is equal to the heat transfer by conduction and evaporation and referred as kilojoule per second or kilowatt. Now, K is the heat transfer coefficient having the unit of kilogram per meter square second. A is the area of contact between the air and water, that is meter square. Hw is the enthalpy of air saturated at water temperature, that is having the unit of kilojoule per kilogram, and Hg is the enthalpy of ambient air and again having the unit of kilojoule per kilogram. Now, there are various steps which are necessary if you use the Markel's theory. Now, you need to combine K and A and assume it a single coefficient of Kga, that is based on the unit volume of pack. Then determination of a mean value of the enthalpy difference or mean driving force. So, a mean driving force is usually illustrated by this particular chart. Now, it has the actual value of enthalpy on vertical axis. Here you see that Hg1 and Hw1, and the range of water temperature on horizontal scale. Now, another step which we need to look into is that to draw the air condition line. Now, here you see that this air condition line. Now, this is equal to the phi is equal to Lw into Cpw into T1 minus T2, and that is equation number 7. Now, what is phi? The phi is the total rate of heat dissipation from the water, and that is represented in kilowatt. Lw is the mass flow rate of water, that is in kilogram per second, and Cpw is the specific heat capacity of water at constant pressure, that is kilojoule per kilogram Kelvin, and T1 and T2 are water inlet and outlet temperature. Obviously, they are represented in terms of the unit of degree Celsius. So, heat gained by the air is phi is equal to LA into Hg1 minus Hg2, and that is equation number 8. Now, where LA is the rate of air flow in kilogram per second, Hg1 is the enthalpy of air outlet, that is kilojoule per kilogram, Hg2 is the enthalpy of air inlet in kilojoule per kilogram. So, if we say that the heat gained by the air and heat dissipated from the water will be equal. So, LW into CPW into T1 minus T2 is equal to LA into Hg1 minus Hg2, and that is equation number 9. Now, one can write this particular equation if we try to rearrange this equation, and that is Hg1 is equal to LW into CPW into T1 minus T2 upon LA in plus Hg2, and that is equation number 10. Now, this if we try to formulate in this particular figure, which is representing the water temperature versus a specific enthalpy, then there is a linear equation of air condition, and this is this particular line. This shows the air conditioning line or air condition line. Now, the vertical distance, this one between the saturation line, this is the saturation curve, and air conditioning line, this gives the difference in the enthalpy, that is the driving force at any cross section through the packing. So, if we take this cross section, this gives you that particular useful information. Now, by using the concept of mean driving force and using a factor that is related to the volume of the pack of the equation for total heat transfer, this becomes phi is equal to kGA into L into A into delta Hm, and that is equation number 11. Now, the L is the height of packing in meter. This A is the area of the packing, the unit is meter square, and this kGA, that is the volumetric heat transfer coefficient, that is kilogram per meter cube second, and delta Hm is the mean driving force, which we have already discussed. This is delta Hm force, and having the unit of kilojoule per kilogram. So, the heat values from the equation number 7 in the previous slides, equation number 7, 8 and 11, they are equal. Then kGA is equal to LA into Hg1 minus Hg2 upon L into A into delta Hm, that is equation number 12. Now, if we equate the equation 7 and equation 11, then we have kGA into L into A into delta Hm is equal to LW into CPW T1 minus T2. And if we try to rearrange this thing, then it becomes the kGA is equal to LW into CPW T1 minus T2 upon L into A into delta Hm, and that is equation number 13. Now, in practical situation, the values for Hg1, Hg2, LW, LA, T1 and T2, they are known. The air conditioning line or air condition line can be drawn by connecting the point Hg1 and Hg2. If you see that this is the delta Hm which we were talking about. Now, by using the water temperature on the horizontal scale, it is possible to mark off the driving force at the top and the bottom of the tower and mean point. Now, for the calculation of F and mean driving force, a chart device by Stephens is shown here. Now, 3 driving force are designed on this chart, and that is Y1, Y2 and Ym, and the values obtained from the enthalpy chart must converted into the ratio of ym is to y1 and ym is to y2. Now these two ratios which we have represented in this chart, vertical and horizontal axis, enable the factor F that to be read off and the mean driving force to be calculated as per this following mathematical equation, that is delta Hm is equal to F into Ym, and that is equal to F HWm minus Hgm, where delta Hm is the mean driving force which we discussed about, F is the Stevens factor, this one is the Stevens factor, and HWm, that is the enthalpy at mean position on saturation line, and Hgm is the enthalpy at mean position on air condition line. Now let's talk about the volumetric heat transfer coefficient, and that is Kga is equal to C into Lw up over A to the power m into La over A to the power n, where Lw and La, they are the water and air flow rate, and that is kilogram per second, and A is the horizontal cross sectional area of the packing, and C, m and n, these are the constants for the pack and usually determined or given by the manufacturer. So in this particular lecture, we discussed about the various design parameters and design aspects and equations for cooling tower design. Again, we have listed with a couple of references for your convenience. Thank you very much.